So just picking up from the last video, I will now show you how to simulate the solar cell under different kind of test conditions. And that's important because the maximum power and efficiency that you're gonna get will be quite dependent. So right now, if we study the front current extraction and rear current extraction, both are set to extract current at each probe point. So here's the front side. Each bus bar has 15 current extraction points. Here's the rear side. Each solder pad has a dense array of current extraction points on the rear. So when we simulate under these conditions, what we really mean is that at a certain applied voltage, for example 500 millivolts, on the front side, each current extraction point is set to 500 millivolt exactly. And each current extraction point on the rear side is set to 0 millivolts exactly. So this is the boundary condition under which the simulation proceeds. And that's pretty close to what you would get if the cell were measured under an IV tester, with probe bars aligned to the bus bars, each probe bars carrying 15 contact pins to make contacts to these 15 current extraction points on the front bus bars. And then on the rear, there would also be contact pins that are specifically making contacts to the soldered pads. So if we were to run the simulation under this condition at a certain voltage, we wind up with very close to 500 millivolts where the bus bars are in terms of the diode voltage. So the front voltage is pretty much the same way, and the rear voltage is very close to 0 at the solder pads. And then anyway, it wouldn't deviate very much from 0 all over the rear plane because of its conductance. So we recall that when we did the IV curve under this condition, we're getting a fill factor of about 78.1%. Now let's contrast this to the situation if we have changed the contacting conditions. In many IV testers, the rear contact is actually a full area metal, like a copper chuck with a uniform surface. Then in this case, we would expect there to be current extracted practically out of every point along the rear cell plane, and that the voltage would practically be the same everywhere on the rear side. We can simulate this either by making the value of the rear metal sheet resistance into a very low value, as well as for the rear solder pads. Now if we rerun the simulation, we get a slightly higher fill factor compared to before, which was 78.1%. Another way to simulate the same thing, which actually speeds up computation time, is to actually change the rear current extraction condition to full area rear chuck contacting. So if we do it like this way, then literally the rear boundary condition is that 0 millivolt is applied to every single node on the rear plane, so that practically every node is itself a current extraction point. If we run the IV curve under this condition, again we get some slight gain in the fill factor, and now it's 78.42%. Now it's not a perfect approximation because actually close to the cell edges there is a 1 millimeter gap that doesn't have metal contact, and that is just the silicon wafer which has a sheet resistance of 150 milliohms per square. So technically that part of the solar cell should not be shorted to the test chuck. So approximating it this way, we are tending to overestimate the fill factor by just a little bit. So for people who only deal with solar cells, maybe these different contact conditions are all that they might care about. But for those who are more interested to predict how the cell behaves in a module, then it becomes very important to also simulate its performance with soldered ribbons at the probe points. So here we're just going to restore the metal sheet resistance values to where it was, as well as the bus bar sheet resistance. Now when we define ribbon connections, what happens is that current are still collected at these current extraction points, but from there the current has to continue its journey down the ribbon all the way to the bottom end of the wafer for the front side. And now if we simulate 500 millivolts, what that means is 500 millivolts is applied at the ends of the ribbons on the front side. On the rear side, 0 millivolts is applied to the top of the ribbons. So current would be flowing in from the top to the bottom on the rear side as well. Depending on the polarity of the cell, that would be the case if it were an N-type cell. For P-type, current actually runs upwards on the rear plane as well as upwards on the top plane. Now since we have introduced ribbons, we also have to set the ribbon properties. So notice that the optical shading now becomes 7.18% because the ribbon width is 2 millimeters. Before the ribbon, the optical shading was 6.24, so we've added quite a bit of shading by this white ribbon. Typically we would actually want the ribbon to be about the same width as the bus bar so as to not introduce too much additional shading. Ribbon shift resistance might be something like 0.07 milliohms per square. Contact points resistance in this context means the contact resistance at the solder joint, but we're just going to leave it at 0 for now because generally a well soldered point should be having an excellent contact resistance. So we do the same thing for the rear side. We set the ribbon width. So let's run the IV curve again and have a look. So obviously here the fill factor has dropped to 76.18%, down from 78.1% of the cell tested in an IV testing condition. And that's obviously due to this extra series resistance introduced by the ribbons. And now, if we go near the MPP and rerun the simulation of the voltages, we see a different pattern. So on the rear side, we can see the effect of the voltage drop in the ribbon. In the front side, it's not as obvious because of this kind of grain contrast, but there is a gradual voltage drop as we move current down the ribbon. So that is in summary the different electrical connection schemes which you can run Griddler at. And often that's a very good way to understand and compare what the cell device characteristics are under different conditions.